We're now going to forget whether the sets we deal with come from shingled documents or any other source and concentrate on the sets themselves. We'll learn the formal definition of similarity that is commonly used for sets. This notion is called Jacquard similarity. We'll then learn how to construct signatures from sets using the Minhashing technique. And we'll prove the strong relationship between the similarity of the signatures and the sets they represent. Let C1 and C2 be two sets. Their Jacquard similarity is the size of the intersection of these two sets divided by the size of the union. We'll use sim as the function representing the Jacquard similarity. For example, these two circles represent sets. There are three elements in common to both sets, so the size of their intersection is 3. And there are 8 elements in the union, so the size of their union is 8. The Jacquard similarity of these sets is the ratio of the sizes of their intersection and union, or 3/8 in this example. We're going to be dealing with large collections of sets, and it is useful to think of these collections as represented by a single Boolean matrix, even if the collection is not likely to be stored that way. First, we assume that there is a universal set from which the elements of all sets are drawn. For example, if the sets come from k-shingling documents, then the universal set is the set of all possible sequences of k characters, or the set of all tokens if we hash the shingles. Each element in the universal set is represented by a row of the matrix, and each set in the collection is represented by a column of the matrix. The matrix has 1 in the row for element E and the column for set S, if and only if E is a member of S. Otherwise, that entry is 0. The column corresponding to a set S is the characteristic vector of the set S, the vector with 1s only in the positions that correspond to the members of S. We shall often talk about the Jacquard similarity of two columns. From each column, form the set represented by the column, the set consisting of the rows where the column has 1. Then the Jacquard similarity of the two columns is the Jacquard similarity of the sets they represent. It is important to note that in typical applications the matrix is very sparse. It has many more zeros than ones. For example, we choose K for k-shingling so that documents have relatively few of the possible shingles, which translates into columns having many more zeros than ones. For another example, suppose the matrix represents the books bought by Amazon customers. Rows are the books and columns are the customers, and customers are similar if they buy many of the same books. Typical customer buys only a tiny fraction of the books Amazon sells, so again we would expect the matrix to be very sparse. Here are two columns, C1 and C2. They're not sparse because it's hard to do small examples when most entries are zeros. However, the calculation of their Jacquard similarity is simple. There are 2 rows where they both have 1, so the intersection of the sets they represent is of size 2. And there are 5 rows where at least one of the columns has 1, so the size of the union of the represented sets is 5. Thus, the Jacquard similarity is 2/5 of 40%. In general, you can compute the similarity of two columns by counting the number of rows where both have 1 and dividing by the number of rows in which one or both have 1. Our goal is to describe how minhashing of sets or matrix columns works and to show that we can deduce the similarity of the sets or columns by looking at the signatures that result from minhashing. Our first step will be to observe that given 2 columns, we can find 4 different kinds of row depending upon which bits are present in that row. For example, a type A row has 1 in both columns. Notice that if the matrix is sparse, most of the rows will be of type D, with zeros in both columns. I find it useful to abuse the notation and use A, B, C, and D also as integers representing the number of rows of types A, B, C, and D in the matrix. We can express the Jacquard similarity of 2 columns in terms of the count of the row types. That is, the similarity of columns C1 and C2 is A divided by A plus B plus C. The reason is that A is the number of rows in the intersection, and A plus B plus C is the number of rows in the union. We're now going to define minhashing. Each Minhashing hash function is associated with a permutation of the rows of the matrix. We don't physically permute the rows. That would take much too much time. We just imagine that the rows are permuted. The definition of the min-hash function h associated with a permutation is that h of a column C is the number of the first row in the permuted order in which that column has 1. To create a signature for each of the columns of a matrix, we pick some number. About 100 is often a good choice of permutations, and use their associated min-hash function, say h1 through h100. For each column, the signature is the sequence of row numbers we get when we apply each of these min-hash functions in turn to the column. It is important to remember that for the entire matrix or collection of sets, we select the min-hash functions once and apply the same min-hash functions to each of the columns. We can think of the signatures as another matrix. The columns of the signature matrix correspond to the columns of the original matrix, that is, to the sets in the collection, while each row in the signature matrix is the result of applying one of the chosen min-hash functions to each of the columns. Let's look at a little example that should make things clearer. Here's an example matrix with 4 columns and 7 rows. Okay. And here's a random, well, quote, random permutation of the rows. The 5th row is the first in order. That's this. And the 6th row is next. And the top row is third, and so on. We construct the first component of the signature for each of the columns using this permutation. We start with the row ordered first, that is row 5. And this row has 1 in the second and fourth columns. And thus we give columns 2 and 4 their first min-hash value. It is 1, and that appears here. Okay, because the first row in the permuted order is surely the first in that order to have a 1 in these columns. We still don't know about the 2's in the first row of the signature matrix, these and this. We'll discover those next. So now we proceed to row 6, which is the second in the permuted order. And this row has 1's in column 1 and 3. It happens that neither of those columns has been assigned a value yet because we haven't encountered a row in which either of those columns have 1. But they both get the value 2 because the second row in the permuted order, but not the first row in that order, has 1 in each of these columns. In principle, we have to proceed down the list of rows in the permuted order, but since we've discovered a min-hash value for each column, there's no point in doing so. Here's the second, quote, random permutation and its resulting row of the signature matrix. In this permutation, row 3 comes first. It has a 1 in the second and fourth column, so the second row of the signature matrix gets 1 in those columns. Okay. Now, look at the second row in this order, which is row 2. It has 1 in columns 1 and 4. We can't assign value 2 to column 4 because we already have a value 1. But we don't yet have a value for column 1, so we assign it the value 2 as its min-hash value in the second min-hash function. We still don't know the value for column 3 because neither of the 2 rows examined so far have 1 in that column. So we proceed to the third row in the permuted order, which is row 4. And it has 1's in columns 2 and 4, but both these columns have smaller values already, so we're still not done. So we move on to the fourth row, which happens to be the top row here. And now we find finally a 1 in column 3. So the min-hash value for that column is 4. Okay, and now we're done with this min-hash function. Here's the third permutation and the resulting row of the signature matrix. I'll leave it to you to study the matter and work out why the min-hash values are as shown. Now, the reason we like min-hashing as a way to summarize sets is expressed by the following remarkable property. Suppose we consider all possible permutations of the rows and ask, for what fraction of the permutations will the min-hash values for the two columns C1 and C2 be the same? It turns out this probability is exactly the Jacquard similarity of the columns or the sets they represent. Okay. Now, here's a simple proof of this fact. Both the probability and the similarity are A over A plus B plus C. We already know that the Jacquard similarity of columns is given by that formula. So why is the probability of the min-hash values being the same also given by A over A plus B plus C? Imagine the rows are permuted in a random order, and imagine going down the two columns in this order. Let's say here's C1, here's C2. Since most entries are 0, we'll probably meet a lot of type D rows. 0, 0, 0, 0, 0, 1. Okay, and eventually we'll come to a row where at least one of the columns has a 1. So let's suppose here's a 1. Now, if we came first to a type A row, then the min-hash values for the columns would agree, because we'd have a 1 here. Okay, and they would both get this row as the min-hash value. If we come to a type B or C row first, where let's say there's a 0 here, then one of the columns, the first one with the 1, gets this row as its min-hash value, but the other column will have to wait until we see a 1, so it's definitely going to get something higher, and they will not have the same min-hash value. Thus, the probability that two columns will have the same min-hash value is the probability that the first row that isn't of type D is a type A row. That probability is the number of type A rows divided by the number of rows of any of the types A, B, or C. That is, A divided by A plus B plus C. Armed with this observation, we can sensibly define the similarity of two signatures. It is the fraction of the min-hash functions for which the two signatures have the same value. It follows that the expected value of the similarity of two signatures is the Jacquard similarity of the underlying sets. Moreover, as we use more and more min-hash functions, the standard deviation of the signature similarity goes down. So if we use several hundred min-hash functions, that is, signatures of several hundred components, we get a small enough standard deviation that we can estimate the true Jacquard similarity of the represented sets to within a few percent. That is good enough for most data mining purposes. Let's revisit our example of computing signatures of length 3 from this matrix. Let's look at some of the signature similarities and the actual column similarities. Remember that similarity means different things for columns and signatures. For columns or sets, it is the Jacquard similarity, while for signatures, it is the fraction of components in which the two signatures agree. So let's look at columns 1 and 3. And their corresponding signatures. Here. The Jacquard similarity of the two columns is 3/4. Notice that there are 4 rows where at least one of these two columns has 1. That is here, 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 and here. And in all but this one, they both have 1. Thus, the size of the intersection is 3 and the size of the union is 4. Now, look at signatures 1 and 3. They agree for the first and third min-hash functions, but they disagree on the second. Thus, the signature similarity is 2/3. Now, 2/3 is pretty close to 3/4, but there is some discrepancy, as we note here. If we look at columns 2 and 4, we again find the Jacquard similarity is 3/4, but here the similarity of the signatures is 1. They are, in fact, identical in all three components. Another interesting example is columns 1 and 2. These columns have an empty intersection, so their Jacquard similarity is 0. It turns out that when the Jacquard similarity is 0, it is impossible for any min-hash function to return the same value for these two columns, as we see again in the white table. Thus, the similarity of these signatures is 0, as it must be. Remember that we have defined min-hashing as if we actually permuted the rows, but it is not really feasible to do so. So let's consider data of modest size where there are 1 billion rows. First of all, it takes a lot of time to pick a random permutation of 1 billion things. You essentially have to generate a billion random integers and do something with each. And representing a random permutation of 1 billion items takes at least 4 gigabytes of space. If we have, say, 100 random permutations, then that's 4/10 of a terabyte just to store the permutation. Okay. And if you try to access the rows of the matrix according to the order of one of these permutations, then you'll have to do many disk accesses to get each row, and that's incredibly time-consuming. Here's how we simulate permutations without actually permuting rows. For each min-hash function, we pick a normal sort of hash function that hashes integers to some number of buckets. We pretend that the position of row R in the permutation is h of r, where h is the hash function. So for each column, we look for that row R in which the column has a 1, and for which h of r is the smallest. More specifically, let's pick some number of ordinary hash functions, say 100 hash functions, one for each min-hash function we want to simulate. Okay. For each column C, we keep a slot for each of the hash functions, called the slot for column C and the ith hash function m of I in C. If we want 100 min-hash functions, then the number of slots is 100 times the number of columns. Our goal is that eventually m of I in C will become the smallest value of h sub I of r, for which column C has a 1 in row R. That is, we suppose that the ith min-hash function orders rows by the value to which h sub I sends each row. Notice that this ordering is not exactly a permutation. It's entirely possible that h sub I maps 2 or more rows to the same value. But if we make the number of buckets into which h of I hashes very large, larger than the number of rows, then the probability of a collision at the smallest value is very small, and we can ignore the probability of a collision. So here's the algorithm in a nutshell. The outer loop is on the rows. Okay. For each row R, the first thing we do is compute each of the perhaps 100 hash values h sub I of r. That's this. Then we loop over all the columns C, and if column C does not have a 1 in row R, then we do nothing for R and C. Okay. But now suppose matrix M has 1 in row R in column C. Then we're going to loop over the index I for all the hash functions. And for each of these perhaps 100 values of I, we check whether h sub I of r is smaller than the smallest value currently in the slot for the hash function hash function I in column C. If that is the case, then we replace that slot by h sub I of r. We take m of I and C to be infinity initially, so the first row in which we find that has a 1 in column C surely is placed in that slot. Also note that it is important we compute h sub I of r only once for each hash function in each row, outside the loop over the columns. That was this. So let's do a little example. Our matrix has only 2 columns and 5 rows. That's this. We're going to use 2 hash functions. That is, we compute signatures of length 2. The 2 hash functions that we use are shown here. Each maps integers to 5 buckets. The first, which we call h of x, maps any integer x to x modulo 5. That is the remainder when x is divided by 5. The second, g of x, computes 2x plus 1, and again takes that modulo 5, takes the remainder of 2x plus 1 mod 5. Okay, we're ready to compute the 2 components of the signatures for each of these columns. Remember that initially we assume all slots are infinity. Begin by looking at the first row. And we find h of 1 is 1 and g of 1 is 3. Modulo, take them all modulo 5, so 3 modulo 5 is in fact 3. Now, row 1 has 1 in the first column but 0 in the second column. Therefore, the second signature is not changed, and both its components remain at infinity. But the first signature is changed to the values of h of 1 and g of 1, that is 1 and 3. Okay. Now consider the second row. H of 2 is 2, and g of 2 is 5 modulo 5, or 0. Since column 1 has 0 in the second row, we do not change its signature. But column 2 has 1 in row 2, so we replace the infinite values in its signature by 2 and 0. Next, the third row. H of 3 is 3, and g of 3 is 7, modulo 5, which is 2. There is 1 in row 3 of both columns, so both signatures are candidates for being lowered. However, h of 3 is 3, and the first components of both signatures are already lower, 1 and 2 respectively. So we do not change either first component. Now, g of 3 is 2, so we might change either second component. For the first signature, the current value is 3, so we lower it to 2. But for the second signature, the current value is already 0, so we leave it at 0. H of 4 is 4, and g of 4 is 9 modulo 5, which is 4. And since 4 is larger than any of the current slots for the first column, no changes are made. Finally, h of 5 is 5 modulo 5, or 0, and g of 5 is 11 modulo 5, or 1. Only the second column has a 1 in row 5, so we can only change its signature. Since h of 5 equals 0 and the old value of the slot for h is 2, we change it to 0. But the slot for g already has 0, which is lower than g of 5, which is 1, so no change is made there. Thus, the final signatures are 1, 2 for the first column, and 0, 0 for the second column. Incidentally, notice that the two signatures disagree for both components, so they estimate the Jacquard similarity of the columns to be 0. And that's off by a little, since, as you can see, the true Jacquard similarity of the columns is 1/5. One last detail is worth mentioning. The algorithm we describe assumes we can visit the matrix row by row, but often the data is available by columns and not by rows. For instance, if we have a file of documents, it's natural to process each document once, computing its shingles. That, in effect, gives us one column of the matrix. If so, we need to do one preliminary step. Sort the data so it is organized by row. That's not hard. Start with a list of row-column pairs where the ones are, initially sorted by column, and sort these pairs by row.